Hello everyone, it's my pleasure to give a presentation here. My name is Shiyan She. As a student whose major is Model-Based Systems Engineering, I'd like to introduce my paper. The title of the paper is Model-Based Systems Engineering, Supporting Integrated Modeling and Optimization of Reader Cabin Layout. As the PPT shows, my presentation is mainly divided into 4 parts. The first part is the introduction and the problem statement of the paper. Then I will highlight the thematic modeling and optimization of reader cabin layout. In the third and fourth parts, I will introduce the case study and discussion, inclusion of the paper. First of all, I will introduce the introduction and the problem statement of this paper. The work of the paper is arranging device in the reader cabin reasonably by MBSE method. As shown in figure B, A, B, C indicates the type of device. Each device has the textures of quantity, length, width, and height. Then, place this device in the tank and lay them out, as shown in figure A. UAV reader is a complex system, and the design of the UAV reader cabin is challenged because its design process is involved with many layout configuration parameters and constraints. At present, there are 3 main problems when designing the layout of reader cabin. Firstly, the document-centric reader layout design increased the designer's difficulty in understanding the architecture of reader layout and gaps among the reader engineers and UAV engineers. Secondly, the layout design of reader cabin is based on empirical approach, which lacks capabilities for generating layouts automatically and rapidly. Third, during the interactive design of UAV reader cabin among UAV engineers and reader engineers, consistent management between reader cabin design and reader layout simulation cannot be supported in an appropriate way. Model-based system engineering is an emerging technology that supports the development of a complex system. So, in this paper, MBSE is used in reader cabin layout. Through the above context, this paper makes use of MBSE approach and semantic modeling to support the reader cabin layout optimization and takes the model as the primary reference to manage consistency across the design parameters of all devices. By integrating with the simulation optimization algorithm and optional layout can be generated, the optimization results can be configured to the MBSE models in order to manage consistency between design models and optimization models. Secondly, I will introduce the semantic modeling and optimization of reader cabin layout in this paper. In order to support the MBSE process for reader cabin design, the framework of M0 to M3 describes the mathematical models, and the real world. Mathematical models refer to the 6 key elements, including graph, object, point, property, relationship, and row, which are used to construct math models. In this paper, math models are constructed based on the 6-mile specification. Math models are the model compositions for developing models. The models are used to describe the real world. Based on the GOPPRR mathematical models and M0 to M3 framework, the common language is a semantic modeling language to describe mathematical model, and models. In the common language, It provides concrete syntax and abstract syntax to describe the math models and models using a textual, semi-formal approach. Through common language, math models are developed based on the SysML specification to support an RFLP requirement, function, logical, physical, and BSE approach. RFLP allows the definitions of product elements and their relationships at different levels of abstraction. For example, using the RFLP approach, requirements R refer to requirements associated with systems and subsystems. In order to support requirement formalism, we construct the meta models, including the requirement diagram based on the SysML specification. In the same way, we construct the rest of meta models and models. As shown in this figure, we adapt MetaGraph to construct a common language library for meta models. Moreover, in MetaGraph, the comma script for defining code generation rule is developed. When defining the code generation script, mapping between model element and the expected output table element are created based on the above mappings. The common language script for code generation is compiled by the comma compiler and is executed by the code generators. Then, the expected output tables are generated. Finally, the genetic algorithm toolkit in MATLAB is executed by loading the input table. After obtaining the optimization results, referring to an optional layout including the space coordinate of each device, a mat file with such information is generated. Then, a developed model synthesis toolkit loads the information in the mat file and configures the parameters in the common language model through MetaGraph APS. In the comma models, device properties of the device space coordinates are known in the reader cabin layout parameter diagram tool. After optimization, known values are changed to concrete spatial coordinates. Through the model synthesis toolkit, the property value in the common language is synchronized for the optimization results. Thirdly, I will introduce the case study and the discussion of this paper. In this paper, a UAV reader cabin case is proposed to evaluate our proposed semantic modeling approach. As shown in this figure, the RFLP requirement functional, logical, physical approach is used to build the comma models for the UAV reader cabin layout MetaGraph. Requirement diagram models is created to describe the functional and performance requirements of reader cabin. The use case diagram and activity diagram models are created to describe the use case and the function flow of reader detection. State machine diagram and the sequence diagram models are created to describe the data processing workflow for reader detection. Then, block definition diagram and internal block diagram models are developed to describe the physical structure of the reader compositions, particular for reader cabin. Moreover, one parameter diagram 1 models is used to define each device parameters, including length, width, height, quantity. Referring to one object instance in the internal block diagram model, another parameter diagram model is used to define the space coordinate parameters of each device, referring to one object instance in the internal block diagram model. For the case study, we create 8 graph meta models using 649 lines of common language and 9 models using 632 lines of common language. Before the optimization, the coordinates of device are known. Then, through the modeling synchronized toolkit, the parameter diagram models are configured based on the optimization results. In summary, the contribution of this paper is to use the semantic modeling based on common language and the RFRP approach to formalize the reader layout to implement optimization for reader layout automatically through the code generation and model synchronization. Finally, is the summary of this paper. This paper mainly makes use of MBSE to optimize the layout of the reader cabin and to support consistent management of design parameters, MBSE models, and optimization model. Thank you.